So an electrochemical cell is a battery which is powered by connecting two redox reactions into a circuit using some wires. So we have two redox reactions here, redox half reactions here, and we will try to put them in this container. So here we have inserted a zinc electrode and a copper electrode into a solution containing both copper sulfate and zinc sulfate. What is going to happen? Although copper is not going to spontaneously dissolve in water because the free energy of copper metal under these conditions is lower than the free energy of copper ions, but the zinc is going to dissolve according to this reaction and will produce two electrons. So zinc will produce two electrons as we saw earlier. And these two electrons will be immediately picked up by these copper ions. But no current will be produced because there is no electron flow. In order to obtain electron flow, we must therefore separate these two reactions into two different compartments. So let's try to do this. This is shown in this figure here. So let's look at the left hand side of this figure right here. Now zinc dissolves in water as zinc ions and releases two electrons, and these two electrons can flow to the copper electrode where copper ions can absorb these electrons to become solid copper. However, no sustained current can flow unless the circuit is somehow completed. In order to complete the circuit, we can connect these two compartments. But if we just do that, then copper ions from here will flow into this compartment and will grab the electrons. So there will be no flow of current. Essentially, this is what a short circuit is. So instead of making a completely permeable connection between the two compartments, we make what is called a semi-permeable bridge. This semi-permeable bridge does not allow the flow of zinc or copper, but it does allow the flow of sulfate ions. So as soon as two electrons flow along this direction, a single sulfate ion can move across, and thus current can flow in this circuit. Now, according to convention, the electrode which loses electrons is called the anode, and the electrode which gains electrons is called the cathode. The representation of this electrochemical reaction can be written or is written in the following way. So the left hand reaction is where zinc loses electrons and becomes zinc ions. And then we have two vertical lines. On the right hand side, copper ions which were in solution get converted to solid copper. In both half reactions, the spontaneous reactions are written from the left to the right. So copper ions can become solid copper spontaneously, and solid zinc can become zinc ions spontaneously. When the concentrations of zinc sulfate and copper sulfate, or zinc ions and copper ions, are 1 molar or standard concentrations, then the electrical potential generated by this electrical cell is called the standard cell potential. And this is typically at a standard temperature of 298 Kelvin. In that case, the electrochemical reaction will be written in this manner. Now we have 1 molar concentration of zinc ions and a 1 molar concentration of copper ions. The total standard cell potential, this circle here denotes standard, generated by this electrochemical reaction is given by what is called the reduction potential of the right hand reaction minus the reduction potential of the left hand reaction. These standard reduction potentials are measured relative to a platinum hydrogen electrode, and you will do this in the laboratory, in laboratory number 2. The standard reduction potentials are called reduction potentials because they all involve reduction of an ion to a solid state, even though the process may or may not be spontaneous. So for example, the standard reduction potential for copper is written in this manner. And it turns out that the reduction potential is 0.34 volts. This is spontaneous. However, even though the acceptance of electrons by zinc ions is not spontaneous, this is how the standard reduction potential is written. And for this half reaction, the standard reduction potential is 0.762 volt, but with a negative sign. Now we have seen that the actual reaction is zinc plus copper ions forming solid copper plus zinc ions. So in order to arrive at this reaction, we can reverse one of the reactions above, which is the zinc ion reaction. And then we have 2 reactions which can be written as now when we reverse the reaction, of course, we have to reverse the sign of the standard reduction potential. Now this becomes plus 0.762 volt. For copper, the reaction is still the same. And the standard reduction potential is 0.34 volts. If you add these 2 reactions, you can arrive at this reaction, and the standard cell potential for this reaction is simply the sum of this and this number here. .102 volt. So this is the cell potential which will be generated under standard conditions if you connect a zinc electrode and a copper electrode by a wire and a semi-permeable bridge, which can, for example, let sulfate ions pass through them. In the next part of this lecture, we will look at the relationship between the standard cell potentials and